Hello guys, good day to you all. Good day to you, and you are welcome to our class for today. I hope you are all doing good and you are having a nice time wherever you are. So for this particular class, we are going to be looking at atomic spectra. Okay, so we're going to be looking at atomic spectra. So please get your writing materials ready, and then so that we can go straight to the class for today. So for today's class, we'll look at different spectra of spectra of atoms, and we'll also look at photoelectric effects. Then we'll do some calculations on using equation or Einstein equation of we'll look at work function and the energy that is emitted by an electron that is ejected from the surface of a metal through photoelectric effects. Okay, so if you for you to enjoy this class, please just get your writing materials ready so that we can go straight to the class. But before then, if you are a returning subscriber, you are welcome to our class. Please invite your friends so that they can also enjoy what you are enjoying. Um, Help us to share our video on different social media platforms. All right, so please, if you are just coming to this particular channel for the first time, please subscribe to our channel. Click on the notification bell so that when we upload a new video, YouTube will notify you. Also, give us a like, give us a thumbs up, and help us to advertise this channel. So this is your online physics class, and I remain Otobo Michael. So you're welcome to our class today. Alright, so today we're looking at atomic spectra. So if you are ready, please let's go. So every gas atom or a gas atom, when excited by heating or passing an electron through discharge tube, gives off light. The light emitted by this atom is characterized by specific wavelength and frequency, and that light is called line spectra. Okay, it is called line spectra. So a series of line spectra are produced depending on the nature of the substance. So we have different types of spectra. We have the emission spectra and absorption spectra. So we have these two types of spectra: emission spectra and what? Absorption spectra. So what is an emission spectra? Electron moving from a higher energy level to a lower energy level produces emission spectra. There are three types of emission spectra. One is line spectra. Okay, so line spectra, this spectra consists of lines of different colors with well-defined lines, each having a particular frequency or wavelength. It is produced from excited atoms from burning gases. So if you look at this picture below, you will see the different line spectra of different gases that are burning. So this is for hydrogen, this is for helium, this is for neon, this is for sodium, and this is for mercury. Okay, so this is what is known as a line spectra. Okay, so beside light spectra, we also have continuous spectra. This spectra consists of light of all colors or wavelengths, e.g. incandescent solid tungsten lamp. The atoms in the metal are closely packed together. The individual energy levels merge together, hence the emitted lines overlap and form a continuous spectrum. So if you look at this, you will see that this spectrum is continuous. There are no definite bands because the individual spectra, they overlap one another. So you now have a continuous spectra. So this is like a picture of a continuous spectra. Then we now have the band spectra. The band spectra consists of bands with each band composed of series of lines. So you can see this band, this is a band having series of lines and all like that. Like oxygen and carbon dioxide produces band spectrum. So these are band spectrum, okay? So these are examples of band spectra. Then we have absorption spectra. This occurs when light passes through a cool gas and certain wavelength of light are absorbed, which gives series of dark lines, each corresponding to one of the wavelengths absorbed. Experiment shows that each element absorbs exactly those wavelengths they emit when they are hot. So you have this is an absorption spectrum of you have chlorophyll, you have chlorophyll A, chlorophyll B, and carotenoids. Okay, so these are examples of so these are the types of atomic spectra. Okay, so we have the emission spectra and then the absorption spectra. We have looked at the different types of emission spectra: line spectra, continuous spectra, and band spectrum. Then we have looked at absorption spectra too. Okay, so now we are going to look at photoelectric effects, and then photoelectric effect is the phenomenon that discusses the ejection of electron from a metallic surface when it is radiated by UV light. Okay, so as a student, you should be able to draw, you should be able to sketch the drawing. Maybe if you are asked to describe the photoelectric effect, what you need to do is just draw this tube, then have your this is your metal that is being irradiated with by UV light. Then this is the cathode. Then you have your anode where the electron streams to. Then complete your circle drawing, and then this is your ammeter for showing that electrons are flowing. Then you have your voltmeter here, and this is your battery. Okay, so you just complete this drawing, and you what you need to do is just write some little theory on this, and you have your full mark. So electrons are ejected or emitted from metal surface when electromagnetic radiation of sufficient frequency falls on a metal. Right, so photoelectricity is thus the emission of electrons from a metal plate when it is illuminated by light. That's what I said before. Now, since the anode is positive with respect to the cathode, electrons will stream to the anode. So the ejected electrons by this UV light will stream to the anode. Now, as the electrons are streaming, the ammeter will indicate that electricity is flowing. Okay, so the maximum kinetic energy of the emitted electron depends. Please take note of this. The maximum, this is a jam question. Okay, I've seen it before. That's a jam objective question. The maximum kinetic energy of the emitted electron depends only on the frequency or wavelength of the incident light and not on the intensity of the light. The statement is very key, and I want you to take note of it. Okay, so the kinetic energy of the emitted electron depends only on the frequency or wavelength of the light and not on the intensity of of the of the light. Okay, so another thing that I want to look at is the work function. The maximum energy needed to pull out an electron from the surface of the metal is called the work function of the metal. So take note of this. The work function WO is the maximum energy needed to pull an electron from the surface of the metal. Then the threshold frequency and threshold wavelength is the minimum frequency or wavelength that must be exceeded for the electron to be emitted. These are definitions that you need to know, please. These are definitions that you should know. the threshold frequency and threshold wavelength, they are the minimum frequency and wavelength that must be exceeded for an electron to be ejected. Is that okay? So when a photon or quanta of light energy is E or HF is incident on a metal surface, part of the energy is known as work function, and this energy is used to liberate the electron from the metal surface, as we said before. Then the remaining energy is used to accelerate the electron from when it has been released from the metal surface. So you have two energy there. The total energy is equal to the sum of the energy required to liberate the electron and the energy required to accelerate, or the kinetic energy of the ejected electron. And this leads us to this Einstein equation. Okay, so the Einstein equation helps us to understand that when an electron is ejected from the surface of a metal, the total energy is equals to the work function plus the kinetic energy. Okay, so this is what I'm talking about, that the energy of the photon is equals to the work function plus kinetic energy, as E is equals to EO plus half mv squared. Remember that the work function of the emitted electron is equals to Planck constant times the threshold frequency, while energy is equals to the Planck constant times the frequency of the emitted electron. We said threshold frequency is the minimum frequency that must be exceeded for the electron to be ejected from the metal surface. So if you combine these equations together, you are going to have E is equals to HF, which is this. WO is equals to HFO, which is the work function, and then you have the kinetic energy, which is EK. Alright, so you need to take note of this equation, and this equation that you have can equally be written as, now if you make the kinetic energy the subject of this equation, assuming you're looking for kinetic energy, you have that the kinetic energy of the liberated electron half mv squared will be equals to HF minus HFO. So this particular equation is the Einstein equation of photoelectricity. This is the Einstein equation of photoelectricity, right? Okay, so what I've said before is what I still summarize here. The energy of a photon is equals to work function plus kinetic energy, and E is equals to W plus half mv squared. So still that to be equation 1. Work function is this, and energy is equals to this. So you can write this together to have this. Remember when we talked about electron volt, we said that the electron volt is equals to half mv squared, which is equals to kinetic energy. So we can actually also change this half mv squared to EV to give us this equation 3. Okay, now also remember that threshold frequency can also be written as C lambda over lambda O, remembering that C is equals to lambda O times FO. So FO can also be given to us to be equals to, sorry about that, C all over lambda O, right? So you can actually substitute this into where you have your FO here. Okay, so you can substitute this into this part of the equation, and then you have equation 4. All right, so these are how you can derive the different equation. Now we have that W is equals to HFO, which is equals to HC over lambda O, which is equals to work function, right? And we have said that FO and lambda O, they are the threshold wavelength and threshold frequency. The minimum wavelength that has to be exceeded for the electron to be ejected is threshold frequency or threshold wavelength. Remember, while the maximum energy to remove the electron is equals to work function. Remember these simple definitions. Okay? Remember these simple definitions. They are very, very important and they are very key. So we have said that from this equation you can actually write this. Okay, and I said this is the Houston equation of photoelectricity. So remember that kinetic energy, which is half mv squared, is equals to HF minus HFO. Okay, so if you look at all this equation, what we have been able to deduce, or what can deduce, that for an electron to be ejected, the incident light must be of short wavelength but of higher frequency. Okay, so the incident light must be of short wavelength but of higher. Take note of this statement. These are JAM questions, please. These are JAM questions, right? So if you are preparing for JAM, if I tell you that, take note of this point, please note it down. These are JAM questions. For an electron to be ejected from a metallic surface, the incident light must be of short wavelength but of high frequencies, right? So that the photon will have enough energy to be ejected, to eject the electron. So please take note of that, and then so that you have a better understanding. So when we talk about the use of photocell, which are photoelectric effect, we have it in potentiometer, burglar alarm, automatic door, television cameras, sound production, film tracks, and counting devices. So photocell, they are applied in all these instances. All right, so please, it is good that you take note of all this. So guys, having discussed all this, we need to solve some problems so that we'll see how we can apply all those equations, all those many equations that we have discussed. Okay, so let's solve some problems. So this is sample question 1, and it says I calculate the energy in joules of ultraviolet light of wavelength 3 times 10 power minus 7 meters. Take the velocity of light to be 3 times 10 power to 8 meters per second, and Planck's constant as 6.6 times 10 power minus 34 joules second. Alright, so for this particular question, remember that energy of an electron is given to us to be HF, which is also HC all over lambda. So here it said calculate the energy. Okay, so in this particular question, you are given a wavelength, which is lambda, to be 3 times 10 raised to power minus 7 meters. You are given the velocity of light. You are given Planck constants. So substitute into this equation. You will have that 6.6 times 10 raised to power minus 34 multiplied by 3.0 times 10 raised to power 8 divided by the wavelength that is given to you, divided by the wavelength, which is 3 times 10 raised to power minus 7. Okay, so if you work this out with your calculator, you are going to have 6.6 times 10 raised to the power minus 19 joule. Okay, so I'm not really particular about the answer, but I'm particular about the way we solve the problem. So that's what I always want you to take note of. The answer does not really matter, but you should understand how to apply the equation to solve any problem. Is that okay? That's the key thing. Once you understand how to apply the equation, your answer comes out readily. So the answer is just like an icing on the cake. Okay. So this is another one. It says that the work function of a metal is 4.5 electron volts, and the metal is illuminated with a radiation of 6.86 electron volt. What is the kinetic energy of the electrons ejected from the surface of the metal? So in this question, you are given WO, which is work function, to be 4.5 Okay, so that is given to you to be 4.5 electron volts, please. Then you are giving the energy of radiation is given to you to be equals to 6.86 EV. You are asked to find EK. That's what you're asked to find. Now remember, we said that energy is equals to what? Work function plus kinetic energy, or EK as the case may be. That's what we said. And we said that EK is equals to what? E energy minus work function. So if you substitute into this equation, you are gonna energy is 6.86 minus work function, which is 4.5 bracket EV. Please don't mind my EO. Alright, so if you work this out, you have that your kinetic energy of this electron will be equals to what? 2.21 electron volt. Okay, so that is it. Alright, so that is it. Don't forget that energy is equals to a chef. Alright, so it depends on what you are looking for, but this is a wire question, and I hope this is good to go. I hope we are good to go with this. Okay, so let's see. Try our hand in another problem. Okay, so this is another problem. I want us to look at this critically. This is a WAEC theory question, and let's see. A photoemissive surface has a threshold frequency of this 4.0 times 10 to the power 14 Hz. If the surface is illuminated by light of frequency 5.0 times 10 to the power 15 Hz, calculate 1. Threshold wavelength, 2. Work function, 3. Kinetic energy of the emitted photoelectrons. You are giving the velocity of light, and you are giving a Planck constant. Okay, so in this particular question, I want you to look at the variables that we are giving right? So here you are given a threshold frequency FO. FO is given to you to be 4.0 times 10 raised to power 14 hertz. You are given the velocity of light to be equals to 3 times 10 raised to power 8 meters per seconds. Planck constant you know already. Then you are also given the frequency of the emitted electron, which is F. You are given F. Yes, F is given to you. Alright, which is equals to 5.0 times 10 raised to power 15 hertz. Okay, so the first thing they say you should find is what? They say you should find the threshold frequency wavelength, which is lambda O. So remember we said that FO is equals to C all over lambda O. So which means that lambda O, which is the threshold frequency, threshold wavelength, equals to C all over threshold frequency. So just substituting into that equation, you will have 3.0 times 10 raised to power 8 divided by the threshold frequency, which is 4.0 times 10 raised to power 14. Okay, so if you work that out, you have that your threshold wavelength will give us 7.46 times 10 raised to power minus 7 meters. So that is your threshold wavelength. Is that okay? Then for your work function, your work function is WO. And we said that WO is equals to what? HFO. Remember, W is equals to HFO. Okay, so you can substitute into this equation. You already, H is the Planck constant, which is 6.6 times 10 raised to power minus 34 multiplied by your threshold frequency, which is given to you to be 4.0 times 10 raised to power 14. Alright, so if you work this out with your calculator, you're going to have 2.67 multiplied by times 10 raised to power 19 joule. Okay guys, so this is your work function. Okay, the next thing is kinetic energy of the emitted photoelectrons. We said that number 3, remember we said that kinetic energy K is equals to HF minus HFO, where HFO is equals to what? It's equals to the work function. HF is the energy. Okay, so kinetic energy is equals to HFO minus the work function. So you substitute into this equation, you are going to have H is 6.6 times 10 raised to power minus 34 multiplied by frequency, which is 5.0 times 10 raised to power 15 as given to you, minus the work function, which is minus 2.67 times 10 raised to power minus 19. So guys, if you punch your calculator and you work all this out with your calculator and you subtract this, you will have that the kinetic energy is equal to 3.0, approximately 3.048 times 10 raised to power minus 18 joules. This will be your kinetic energy of the ejected electrons. Okay, so you have this as your work function, you have this as your threshold wavelength, your work function, and this is your kinetic energy. So I think this question actually summarizes most of the things that we just discussed. Okay, the threshold wavelength, work function, and kinetic energy of the emitted electron. Okay, so this is how to solve problems involving this particular topic. I hope we are following and we are getting traction, right? So very quickly, we'll just look at this topic, stopping potential. It is actually a property of a photoelectron, right? So the stopping potential of a photoelectron emission is given by the electron volt, which is equals to, electron volt is equals to EK, right? Which is equals to kinetic energy. That's what we said before. And from our previous discussion, we said that electron volt, which is kinetic energy, is equals to HF minus work function. So the V is the stopping potential. So stopping potential V is equals to HF minus W all over E, which is EKO. Okay, which is, the whole of this is equals to this. So which is equals to EK. So it's equals to EK all over electron charge. Okay, so V is the stopping potential in this particular equation. Okay, so E is the stopping potential. All right, so we're going to solve another problem now on these two. So this question says that the maximum kinetic energy of the photoelectron emitted from a metal surface is 0.34 electron volt. If the work function of the metal is 1.83 electron volt, find the stopping potential. This is a jam question. Okay, so here in this particular question, you are given EK to be equals to, you are given EK to be equals to 0.34. Then you are given work function to be equals to 1.83. Alright, so we say that stopping potential V is equals to HF minus work function all over E, or EK kinetic energy all over E. So in this particular question, we need to look for the kinetic energy. Okay, you have been given the kinetic energy already, right? Yeah. In this equation, you have been given the kinetic energy already. So we can actually say that work function V is equals to EK, kinetic energy, all over E. So kinetic energy is 0.34, 0.34 EV all over divided by E. So E can actually cancel that. So you now have 0.34 volt as your stopping potential. So please, I brought this up so that you understand how to solve questions on stopping potential. Okay, so this is your stopping potential. Alternatively, please take notes. Alternatively, you can solve for this stopping potential. First of all, since you already know EK, you know the work function, we remember that EK is equals to HF minus WO. So HF will be equals to EK, I mean to say, sorry, plus work function, right? So you can just put it there that EK is equal to 0.34 plus 1.83 electron volts. So when you add this together, you're going to have 2.17 electron volts. Okay, 2.17 electron volt. So remember that we said that so I haven't gotten that. Okay, so I haven't gotten that. Remember that we said that V is equals to HF minus WO all over E. Okay, so if you substitute the other equation, you're going to have 2.17 minus 0. Or minus 1.83 all over E. So if you work that, you are going to have 0.34 EV all over E. So this cancels out and you will still have the same answer, 0.34 V. Okay, so depend on your preference and the method that is faster for you, you can use to solve this problem. But whatever be the case, you still have the same answer in the two processes. Okay, so that is that. Alright guys, so thank you so much. This is where we draw the curtain and this is your test your understanding page. All these questions we solve similar questions like this, so please try your hands on them. You can reach us through the WhatsApp number that is shown on your screen in case you have any challenge or any problem. Okay, so thank you for being with us so far and we really appreciate you. If you are just joining this platform or if it is your first time of visiting, please, I will encourage you to please subscribe to the channel. Click on the notification bell so that whenever we upload a new video, YouTube will also notify you, right? So thank you. This is Normal Science Tools Online and this is your online physics tutorial. So thank you. See you in our next class and have a nice day. Thanks.